This lesson is about process capacity. Before we get to the concept of capacity, let's take a look at another related concept of processing time. And this is a very simple concept. It's basically the time that it takes for an activity to get completed. So if you take 5 minutes to get the activity completed, that's the processing time. Now, the only complication that you have over here is that that 5 minutes might complete one unit. That 5 minutes may complete a whole batch. Either way, we're going to call it the processing time. And this concept will become a little bit more clearer as we look at a few examples of what do we mean by it being done in a batch versus it being done as a single unit. So just keep this in mind as we move through some of the examples that we're going to look at. Let's take a look at this example of packing cookies. Right? So we have two different stations that are packing cookies, which simply means there are two people who are working in this activity, and each of them is doing the same task. They're packing cookies. Now, the information that we're given over here is that it's 2.5 minutes to pack a single packet. So if you were to be asked what is the processing time, you would say that's 2.5 minutes, obviously. What's the cycle time of this activity? And the cycle time is going to be 2.5 divided by 2, because two of them being done simultaneously gives you 1.25 minutes. And that's the average time between two units of packaged cookies coming off of that activity. Now, if I were to ask you the question, if I give you cookies to pack, can you give me a packed cookie in 1.25 minutes? Your answer is going to be obviously no. It'll take me 2.5 minutes to pack it. But by adding another resource to it, adding more capacity to it, what you have done is you have halved the cycle time. You've taken the cycle time, which was 2.5 minutes if you had only one person. It has become 1.25 minutes because you added one more resource to it. Let's go to the third concept of flow rate or capacity. Now, flow rate or throughput rate or capacity is going to be the reciprocal of your cycle time. You added more people, you added more capacity to that activity. So when you are having a cycle time of 1.25 minutes, you are basically producing 0.8 packets per minute based on 1 divided by 1.25, and that translates to 48 packets per hour. So the important concept you want to remember from here is processing time and cycle time are different, and that flow rate is the reciprocal of cycle time and not the reciprocal of processing time. That's an important thing to remember because that's an easy error to make. Let's take a related example and see how we can think about flow rate or capacity in this example. So earlier we talked about having multiple resources. Here we're going to talk about a resource that makes many units at the same time. And in operations management, we call this a batch. So here you have, in this example, a machine activity such as baking cookies, which hopefully you can all relate to. And we're baking these cookies with one oven that can bake 40 cookies at a time. The time required to bake these cookies, and these are really crisp cookies, and that's why it takes 30 minutes for them to be baked. So the processing time, you're going to say obviously 30 minutes. The cycle time here is going to be 30 minutes divided by 40 cookies being done in parallel. So it's going to be 0.75 minutes, 45 seconds, right? In 45 seconds, are you going to be able to give me a cookie? And your answer is going to be no, I'm not going to be able to give you a cookie in 45 seconds, but I can give you 40 cookies in 30 minutes, giving me an average cycle time of 0.75 minutes. Once again, like we saw in the previous example, the flow rate or the capacity is going to be calculated as the reciprocal of the cycle time. So it's going to be 1 over 0.75, giving you 80 pieces per hour as the capacity. Now, let's take the same example and we'll tweak it a little more as we go further based on another concept called setup time or changeover time. So what is changeover time? It's the fixed time for preparing an activity for its work content. So if you were to think of that baking the cookies example, the way you would think of the setup time or the changeover time is that if you had only one tray for baking cookies, and between every batch you had to clean the tray and then put the dough balls on the tray in order to bake those next batch of cookies. That would be your setup time. So that setup time would be a time that is fixed regardless of the quantity of cookies that you bake. You might bake a whole tray, or you might bake half a tray. The time that it will take to clean that tray is going to be similar regardless of how many cookies you actually put it in the oven. You'll probably have to wash the whole tray and do the same kinds of setup activities, the same kind of changeover activities, regardless of the quantity. Typically in production environments, why do we have setup time? It's because we do things in batches, and you might be making many different products from that same activity, from that same process that you're using. So you'll have changeover between those different products. You'll determine the batch size based on the setup time. So if there's a longer setup time, you'll say, well, I'm going to make a large batch if possible, or I'm going to make many batches of the same thing if possible, so that I don't have to do too many changeovers. So setup time does affect capacity in terms of reducing the capacity. It takes time away from what is available for the actual capacity of what it's actually doing, what the process of the activity is actually doing. So now let's take this concept and apply it to that same example that we had earlier of baking cookies. So we have a machine activity of baking cookies, but now we said we're going to say, in addition to the 40-minute baking time, the 30-minute baking time, we're also going to have a 10-minute setup time. So effective processing time is going to be 30 plus 10, and we're going to say that 40 minutes for the batch. Effective cycle time is going to be 40 minutes for the batch divided by 40 cookies that got done. So effectively, we're getting this done in 40 minutes, and we're saying I'm giving you a cookie on average per minute. Effective flow rate is going to be based on the 1 minute cycle time, and therefore it's going to be 60 pieces per hour. Next, let's look at the cycle time and the flow time of an activity, and how these two concepts are related. So the cycle time of an activity is the processing time of an activity, and we divide it by the number of units that are processed in parallel, whether it's multiple resources or whether it's a large batch. Both of those are saying many units are being processed in parallel, and you incorporate that into this calculation of cycle time. When you're looking at the flow time of a process, when you're looking at many activities that are happening in sequence, and you're adding all of the times of these activities to come up with a flow time or a throughput time of the process, in that case, you are not going to be adding their cycle times. You should be adding their processing times. So it'll be the sum of all the processing times, and on top of that, there might be some waiting time between those processing times. So from a definitional perspective, flow time is going to be the sum of all the processing times plus the time that is spent waiting between each of the activities for which you've added the processing times. Now, let's take this example and look at the implications of what happens when you increase the capacity of a process. So here we have a simple two-step process, and we have cycle time of activity A as being 10 minutes, cycle time of activity B as being 8 minutes. What I'd like you to think about is what is the flow rate of the process and what is the flow time of the process in the current condition, and also when the resource for activity A is doubled. So right now you have one person or one machine being used for activity A, and what if we were to double that? So I'd like you to think about that. Second, what I'd like you to think about is based on this idea of Little's law, which states that inventory is a product of throughput time and throughput rate. When you're talking about it from a process perspective, I want you to think about what is the impact that adding that extra resource for activity A is going to have on the inventory in the system. So take a few minutes and think about this, work through the calculations, and we'll come back and see what we can find from looking at this manipulation of the resource. All right, so we had a two-step process, just to remind you, activity A, activity B, and the question was measure all the different things for the process as is, and then use Little's law and measure the same things for if you were to double the resource at activity A. So before you double the resource at activity A, the bottleneck activity was the activity that took the most time, and that was activity A, which took 10 minutes versus 8 minutes for activity B. So the process cycle time would be 10 minutes based on the cycle time of the bottleneck activity, and the process flow rate would be 1 over 10 or 0.1 units per minute. The flow time would be 10 plus 8, 18 minutes. If you were to double the resource at activity A, now what has happened? The bottleneck activity has now shifted to B. The cycle time for activity A, based on there being two parallel resources, two people doing the same work or two machines doing the same work, you have doubled the capacity, the cycle time has become half, and now the bottleneck activity is activity B. So the bottleneck activity has changed. So if I were to ask you for the process cycle time, it's going to be based on the processing time of activity B, and that's 8 minutes. The process flow rate is now based on that new cycle time of 8 minutes, so it's 0.125 units per minute. What you'll notice is the flow time has stayed the same. It still takes 10 minutes for activity A to get done, whether it's done by the first resource or the second resource that we put into activity A, and it still takes 8 minutes, so it's 10 plus 8, 18. Now let's take a look at the impact that this had on the inventory in the system. You may recall Little's law, which states that when you're looking at a process, the inventory in the system, the average inventory in the system, is going to be equal to the product of the throughput time, the flow time, and the throughput rate or the flow rate. So before we double the resource at A, we have a flow rate of 0.1, a flow time of 18, so inventory of 1.8. After you double the resource at A, the flow rate became 1.125, the flow time became 18. Inventory went from, I'll go back to the previous slide for a minute, it's 1.8 units is what we had earlier when we had not added another resource at A. Coming back to when you added the resource at A, what you notice is that the inventory has actually gone up. It has gone up because you added more capacity into the process, into the system, and that has had the effect of adding more inventory into the system. Well, the question that you should be asking, or you would be asking, is so what, right? You increase the capacity, and all that did was it did speed up the process a little bit. It increased the total amount of free time that exists, so there was excess capacity, and you had ended up with more inventory. So is adding capacity going to be a good thing or not a good thing? Well, what would have been good, what would have been better than simply adding capacity to the bottleneck task here, to the task that was a slower one here, would be if we could balance it out. If we could take the total of 10 plus 8, 18 minutes, and if we could say that each of these activities is able to work at 9 minutes, that would have helped in terms of getting the process a little bit faster, from 10 minutes going to 9 minutes, and at the same time having more control over the inventory that's in the system. So you would have had less inventory in the system.